Okay, let's start. So we will continue our discussion on divide and conquer. We already saw many examples and we finished matrix multiplication this time. Today we'll see some statistical problems. We already started this briefly. We'll finish off that. Moving on to the next one. So statistics is nowadays very important because it appears in lot of important areas like data science, machine learning stuff. But we are just going to look at some basic statistical problems. Okay. The problem is you are given an array of n numbers. It may be sorted, it may not be sorted. So it's given in any order. And we want to find the kth smallest number. Here, k is any integer between 1 and 3. In fact, k is also given as input. Your goal is to find the kth smallest number. Okay. And so, for instance, here is an input array 2, 5, 8, 4, 6. What is the smallest? 2. Second smallest is 4. Third smallest is 5. Fourth smallest is 6. And then finally, right? Problem is clear. And usually the trivial way to solve this is we just sort using any of our favorite techniques. Since we are talking about divide and conquer, we'll use merge sort. Okay? This is an example of divide and conquer. Okay? So we just sort these elements and output the element in the kth location. That will give you the kth sequence. Okay? So how much time does it take? N log n. And we obviously want to do better than that. Okay. For some special cases, we can already see that we can do better than in log n. So let's look at the minimum. Minimum, obviously, you know how to solve it in order of n time. We go of n time. So there are many ways to devise algorithms for outputting the k smallest number. But we are only interested in divide and conquer for this case. So how do you compute the smallest number using divide and conquer? You just split the array into two equal parts. Okay. Find out the minimum of the first part and find out the minimum of the second part and compare those two minimums. Whatever is the smallest, that will be our minimum. Same thing you can do for maximum also. Divide the array into two parts, compute the maximum of the first part, compute the maximum of the second part, and output the larger integer among those. Okay. So Yeah. And how much time does it take? Linear time, right? Because if Tn is the time taken for one part, your recursion will be Tn equal to 2Tn by 2 plus order of 1, because we are just comparing some minimums or maximums. And you can solve this recursion using your favorite method. You will find that 2 of. So the first question is, can we do better than for this? Can you have a, let's say, n over log n or log n time algorithm for minimum or maximum? No, you can't. So why not? Because there are n many elements and you need at least big O of n time to at least read these elements. So if you don't, if you can do it in better than O of n time, you are likely to miss out on some element, and who knows, that might have been the minimum or the maximum, right? Of course, there are some algorithms which, like binary search, that work in O of log n, right? But there we have this assumption that the input array is sorted. So just by making a simple comparison, we could dismiss some of the elements. But here it is not the case. You are given the elements in any order and you want to say something about this array. Okay? So in this case, big O of n is the best possible. You cannot beat that. And yeah, we would like to see algorithms of this type. So minimum and maximum both take big O of n time. Should be clear. What about the second smallest? Tell me some divide and conquer strategy for second smallest. Sorting will take n log n time. We want O of n time for second smallest. Simply traverse the array, but here are you using divide and conquer. Yeah, partition method. Again, you partition the array into two parts, right? In the first half, what you will do? Let's say you found the second smallest in the first half. You found the second smallest in the second half. How do you find the second smallest in the entire? So in this case, let's partition it as 2, 5, 8 in one set, 4 and 6 in the other set. Right? What is the second smallest here? It is 6. Second smallest here is 5. But in the entire array, neither 5 nor 6 is the second smallest. Second smallest is 4. Right? So you see where I'm going, right? So you need to compute both the smallest and second smallest in every half, in each of these halves. Okay. So overall you have 4 elements, 2 from the first half and 2 from the second half. Right? We are storing the smallest and second smallest. Divide that into 3 parts. Okay, you can do that, but let's stick to 2. As I said, this can have many different solutions. Let's look at the simplest. Let's just divide it into 2. So who are the possible candidates for second smallest? From the first half as well as from the second half. So can the third smallest element in the first half be the second smallest in the entire array? No, because you already had 2 elements which are smaller than this guy. So this guy can't be the second smallest. Yeah, 2, 5, 4, 6 in this case. So you take any array of n elements, you will just have 4 elements which are candidates for the second smallest. Correct? And it's just 4 is a constant, and so you can just sort this array and find out the second smallest among these elements. Right? It is a constant size array, and you can do sorting in constant time there. Right? And this technique, there was nothing special about 2. Let's say I talk about the kth smallest, where k is some constant. It could be 5, 10, 20, whatever. You can use the same thing. You divide the array into two parts. You store the smallest, second smallest up to kth smallest, the first part. Store the smallest, second smallest up to kth smallest in the second part. Then just sort this new array of 2k elements. Okay, since k is a constant, you can do this sorting in constant. Okay, so how far can this strategy go? Will it always give us a O of n time algorithm for any k? Yeah, when k becomes very large, you can't. So roughly when k is, let's say, n by log n. Okay. So let's say you have n by log n elements in the first part, or in fact n by 2 times log n. And you have n by 2 times log n elements in the second half, right? So overall you have n by log n elements, and this you can sort in linear time using whatever your favorite merge sort. So when k becomes very large, it is problematic, and we need to devise some other method. Okay, and we will take the most difficult option, which is that k is right in the center. That is called the median. So here, what is the median? It's 5. It is right at the center of this sorted. 2 and 4 are smaller than 5, and 6 and 8 are larger. So I want a linear time algorithm uh, which can find out this median. Okay, so what else can we do using divide and conquer? So, sorry, yeah. So what's the problem with the k smallest number for any k years, right? So let me ask you, what is the n by 4 smallest number in this array? You are given integers between 1 and n, so there are n many integers, and, or in fact, there could be, it could be from a larger, what is a larger range, okay? But there are n many elements, and I ask you, what is the n by 4 smallest number? So what is the strategy we discussed? We divide this array into two parts. Okay, and you find in the first part you find the smallest, second smallest up to n by 4 smallest. In the second part also you do the same. And now you want to find the n by 4 smallest in the entire array. So it could be any one of the n by 4 smallest numbers in the first part and n by 4 smallest in the second part. So totally you have n by 2 numbers which you want to sort. Can you sort them in linear time? No. So that's the main obstacle which is coming. In that when you have larger candidates for this n by 4 smallest or whatever, you have a problem because you don't know how to sort them in linear time. Yeah. So what else can we do? I want to find the median. Okay, so in this case, it's 5. So in fact, we'll use an idea which we have seen before in quick sort. Okay. So what do you do in quick sort? Find some pivot element which is roughly and rearrange this array such that all the elements which are less than pivot element, they are to the left of this element. And all the elements which are larger than this pivot element, they are to the right of. Okay. And there is a standard algorithm. Like given a pivot element, you can always rearrange this array in this nice form. Okay. And in fact, you can do it in linear time without using any express space. You just swap some elements here and there, and you can rearrange this array in the desired form. So what is that algorithm? Let's see. Okay. So first we need to find a good pivot element, X. And then once we have this, let's say we found this pivot element X, and we also rearrange this array such that all the elements which are less than X, they are to the left of X, and all the elements which are larger than X, they are to the right. Okay. So now, what do you know about the kth smallest element? Either it is in the left part or in the right. Okay. And both these parts are smaller than A, so you can recurse on this particular part. So that is our divide and conquer strategy, which we want to use here. But now there are these two obstacles that what is a good X? And given an X, how will you partition in linear time? So let's say I just randomly pick any element to be the pivot. Then what is the worst that can happen? What is the worst time complexity of this? I pick some random element as a pivot element. No. So let's say I'm asking the worst case. Worst case. Yeah, order n square. We go of n square. Because what can happen is there is just one element which is smaller than x and all others are larger than x. So let's say there are n minus 1 elements which are larger than x. So Tn will be Tn minus 1 plus big O of n. You solve that recursion, you will get big O of x. So we need to choose this carefully. Okay, x. And yeah, it is not clear how to choose this. Okay. So what is a good partition for x? So, yeah, of course, if we had the median, the problem is already solved. So yeah, but roughly it should be like n divided by some constant. And yeah, but you don't know the middle element yet. If we knew the middle element, we don't have to do anything else. Right? So we have to settle for some weaker pivot element, but still ensure that the entire algorithm works in linear time. The final goal is to find that median. So in fact, let's say you had something like n over 10 elements which are smaller than x and remaining 9n over 10 minus 1 to account for this are larger than x. Even these partitions are fine for us. Okay? But still, even these partitions, how do we find this pivot element? That is the main question. So again, we will use some divide and conquer strategy for finding this split element or pivot element. So tell me something, divide and conquer for this. Pivot element to be the average of the largest and the smallest element. Okay, that's an interesting idea, but it might fail because how do you know that uh, the average will work? So yeah, I gave you a hint that uh, you have to use some divide and conquer strategy. Yeah, average may not be true always because what happens is, let's say you have some small element here and the rest n minus 1 are all large and this large is big enough so that the average of the small and large is this central element. So again, you are in O of big O of n square. That is even worse than sorting and finding the k element. Okay. So mostly in this course, and we have seen divide and conquer where we split at some central element or divide into three groups of n by 3 elements and so on. Here we are we will be using divide and conquer with smaller sets, okay, in the partition. So I fix some constant 5 and partition this array into sets of size 5. Okay. So there are n over 5 sets. In each set will have size 5. And inside the small sets, you can sort in constant time. So it is very easy to find the median of each of these small sets. Now from these medians, can you compute this uh, split element if you want? Okay, so let's see how to do that. Okay. So even before that, let's say you are given this pivot element and you want to partition this array into two parts. One is less than x, greater than x. Okay. So it's the same algorithm which we use in the partition subroutine in Quicksort. Okay. So what you do is whenever you find the violation that some element greater than x is lying to the left of some element is less than x, then you just swap those two elements. Okay? So here is this algorithm. Let's say your pivot element is at the end. So it need not be at the end, it could be anywhere in the array, but you can just swap those two elements to make sure that it's always at the end. And there are two pointers which will maintain I and j. I is just before the start of the array, and j keeps moving, and I also keeps moving. Okay, I equal to I plus 1 if just compare aj is less than equal to, right? And whenever there is a violation, you just swap these two elements, and finally swap the last element with the element which is in the middle. That will be your pivot element. All elements less than x will be here, all elements larger than x. Okay. So this has linear running time because all these operations are constant time, and this for loop runs for n minutes. Okay. So here is one example. You set I to the beginning of the array and j to be this 3. You compare 3 with 4, 3 is smaller than x. So j moves forward, I moves forward. Okay. Again, you compare this ith element, right? 3 is less than 4, so I moves forward and j moves forward. You have this 3621754. But now you see that this 6 is larger than 4 and 2 is smaller than 4. So here you have a violation. So you need to swap these 2 and 6. Okay. And you consider the next one, it is 6 and 1. Again, there is a violation. 6 is larger than 4, 1 is smaller than 4. So again, you swap this. Okay. And keep on doing this and get a linear time algorithm. So you swap is 1 and 6. Okay. And finally, you swap 4 and 6. So that is a linear time partition. So we know given a pivot element, how to find the partition in linear time. Okay. And the trick is how do we find this partition? Okay. So what we are suggesting is we divide this array into various constant size array. So from one-dimensional array, we are going to two-dimensional array, where the number of rows are some constant. Let's fix it to be 5. So there are n by 5 groups of these 5 elements, and you find the median of each of these 5 elements. Right? And from these medians, we want to find the median of the original array. Okay, so our divided conquer strategy is very simple. We found these medians, okay, and what we are going to say is that you find the median of all these medians, okay, and that we claim is a good split element. So can you see why? So we assume that these arrays are arranged like this is the largest element, this is the second largest, and so on. Okay, because you can always sort them and ensure that it is in this order, right? And the rows are sorted as smallest, second smallest, third smallest, fourth smallest, and so on. So which of the elements are larger than this pivot element? So the arrow is in the wrong direction, it should be in this. Or you can take this way also, it doesn't really matter. So we want to find out how many elements are larger than this or smaller than this. So notice that all these sets may not have 5 elements each. Some of them may have fewer elements as well. Because we don't know anything about the size of the array. Could be divisible by 5, not divisible by 5, we don't know. So which are the elements which are smaller or larger than this? Okay, let's see. So these things are certainly uh, smaller, right? This is the least element, this is the second least element, third least, and so on. These things are smaller, these things are large. Okay, and these things are larger than these things, so they are also uh, larger than this pivot element. Okay, so here is just recap of what we are trying to do. Divide the array into n by 5 groups, each having 5 elements, and possibly one group contains less than 5. Okay. So here the last group, it has less than 5. Sort the elements in each group because there are only 5 elements, so you can do constant time for each group, and there are n many groups. So or n by 5 many groups. So it takes big O. Again, you find the median in each group and put them in an array B. Once you have the medians in each group, you find the median of all these medians. Okay, so there are n by 5 many elements. So this will be Pn by 5. Then once you have found out this pivot element, you apply this partition procedure on it to make two subarrays around x. So on the left you will have elements which are smaller than x, on the right you will have elements which are larger. This will take order n. Okay. So let Q be the index returned by this partition procedure. What is this n1? Is the size of the left subarray. You have which are the elements which are smaller than x. And what is n2? It is the elements which are larger. That is the size of that right. Then you just apply this divide and conquer, which is T of n1, T of n2. This is just constant time, just return. Okay. And what we want to see is what is the running time. Let's just see an example here. 5, 12, 59, 27, 7, 82, and these numbers are given to us. So you partition it into sets of size 5. So in the first you will have 5, 12, 59, 20, 77. And then the second you will have all these things 11, 54, and so on. In the last thing you have just 3 elements. So we sorted the first thing, okay, 5, 12, 20, 59, 77, 10, 15, 27, 69, 82, and so on. You sorted all these, found the median, 20, 27, 16, 31, 37. Right? And there are these 3 elements, 2, 5, 9. And then we found the median of all. So you sort these elements, what you get 16, 20, 27, 31, and 30. 16, 20, 27, 31, and 34. And then you found a median, and that is 27. 27. Right? Now, which are the elements which are guaranteed to be smaller than 27? In this top left uh, half, right? Because these two elements are smaller than 27. This is also smaller. This is also smaller. So all elements which are smaller than these things, they will be smaller. 6, 11, 5, 12. All of these are small. The rest we can't say anything. This could be larger or this could be smaller, but these things are definitely smaller. Okay. So in these 5 elements, you can always find 3 elements in this group which are smaller. Okay. And then we just partition this array into 27 will be at the center, all elements less than 27 to the left, and all elements greater than 27 will be to the right. Okay. This is just our partition procedure. Two. So the main thing is we want to find what is. So first of all, what is the recursion which we want? So we want to find the median of these n by 5 elements which we had. Because we are taking the median of all medians and we had n by 5 groups of 5 elements. So Tn will be Tn by 5 plus maximum of Tn1, Tn2. What are n1, n2? n1, n2 are the number of elements which are smaller than this 27, and n2 is the number of elements which is larger. Okay, so to solve this recursion, we need to know what are this n1 and n2. How many elements are smaller than, right? And how many elements are larger than. So what do we know? How many elements are smaller, which we can surely tell that they are smaller. We saw that the top left half will be strictly smaller, or at most the value of x. If there are repetitions allowed, there could be some numbers which are equal to x. Okay. And what are the elements which are larger than x? So whatever is below x is strictly larger than x. And these elements are also larger than x. It's the way we have designed this. Right? And so all elements which are larger than these particular elements, they will also be larger than x. Okay. So this bottom right rectangle, it will all consist of element larger. And the top left rectangle, this will all consist of elements which are smaller. Okay, so in general, if you have n elements, you are partitioned into n by 5 groups. What is the number of elements which are smaller than this? Right? So the first observation is at least half of the group medians are smaller than this. Right? So this was the median of all medians. So half of the group medians, they will be smaller than x, half of the group medians, they will be larger. Exactly. So there are n by 5 groups. There will be n by 10 group medians, which will be uh, smaller than x. And including this element, there are three more elements which we need to count per group. So there are overall 3 n by 10 elements are smaller. This is just a lower bound. There could be many more elements which we are not counted here. Okay. We just know that at least 3 n by 10 elements are smaller than x. And then we have this recursion. Tn is Tn by 5 plus T3n by 10 plus big O. So the same thing was for larger than x. Right? You had this big O. Okay. And we just assume that this 3 n by 10 is larger than n by 4. You can verify that. Okay. So what's the solution of this recursion? So this is slightly unusual recursion. You won't encounter much, but the thing to notice here is that n by 5 plus 3n by 10. How much it is? 5n by 10. And that is strictly less than n. And you can use whatever your favorite method is, and you see that the solution to this recursion is big O of n. Okay? And in fact, yeah, you have two elements which are of different sizes, n by 5, 3, n by 4, because this was recursive call to selection in step 6. It is executed on 3n by 4 elements. And you can solve this recursion and, yeah, order of big O of n. So great. We have a big O of n algorithm. You can use whatever your favorite substitution is. Yeah, that's entirely up. Okay. So great. We have a big O of n algorithm for finding the pivot element, and we also know big O of n to partition that array those two parts, and then we just apply those that rules. Tn by 5 plus t3 4 plus b. And overall the algorithm runs in big O of n. Okay. Yeah. So that's it. Any questions?
Sir, how can we make this 5 cross 5 sorted array?
Sorry, how can we make this?
That sorted array in which we have to find median. Yes, this array, 2D array.
Yeah. So you sort each of these groups, right?
But the sorting itself will take
No, this is
some.
constant size. They are just 5 elements in each group, right? So overall it will take constant time.
But sir, if there are means more than 5 or means how means
No, so
uh,
deliberately we have chosen these groups to be very small, constant size groups. And there are obviously a large number of groups, but that is fine for us. So you can find all these medians, correct? And
but
find the, yeah.
if there are more than 25 or less than means they which are not a multiple of 5 and we cannot make 5 cross 5. 5 means this 2D array type.
Yeah,
So
yeah. So you can have some elements which are less than 5 in one group.
hmm.
That is not a problem. So very simple in a algorithm, just a little more detail.
Sir, here, why are we not computing the median of the last group?
Um, yeah, so we could have done that, but it's always so there are just constant many elements, right? In every group. So once we have the larger size thing, it's completely fine. Yeah, you can take the mean. So the thing is, I don't know how many elements are there in this group. In this example, I had only three. There could be one or two or whatever, right? Yeah, but you can very well take the last one.
Yes, sir. So, but will it have an effect on the quality of the pivot element we are getting?
Yeah, quality of the pivot element. So I proved to you that it has at least these many elements which are smaller than x, and at least these many elements which are larger than x. And that is some 3n by 5 and whatever we got below, 3n by 10. And then we saw that, okay, this is a good pivot element because the solution to this recurrence is still big O. Okay.
Yes.
And in fact, only this strategy works. I mean, quick sort type of strategy. You can try any other merge sort thing, it doesn't work. That called this. Yeah, you are always welcome to think about alternative approaches. Actually, this is not the only way to find this uh, good split element. There might be other algorithms, but we are just focusing on finding the median of medians. Okay. Are there any more questions? Should we stop here? Sorry, I didn't read that. Up to what length? To what length of an individual group will we have a constant time to sort them? Yeah, that's a good question. Uh, so obviously constant as I realize, right? If you are just looking for constant time, you can't have a, let's say, triple log n size there. By this algorithm, we are getting only the pivot element, and yeah, you are getting the pivot element, you know how to partition those things according to the pivot. And then we just divide it up. Okay, let's stop here.